everyone. I am Marie from the French Competence Center, the CCFR, part of the EuroCC project, and with Pierre Robert from the lab in Annecy. Together, we organize the Grey Scott Thursdays and the Grey Scott School. Welcome to this new session of the Grey Scott Thursdays. Today is already our 8th webinar, I think, out of 18 planned in the series. We're very happy to see that the community keeps growing, so thank you for being here. And you also have access to the replays of all the last webinars on our YouTube channel, so don't hesitate to have a look and also put comments. It helps a lot. As you know, these weekly webinars explore the key topics from the Grey Scott School curriculum and gradually prepare the ground for the summer school. A quick reminder, the registrations for the Grey Scott School will open very soon, next week, so keep an eye out. Don't forget that the school is very flexible. You can register for 1 or several days, depending on your interests, and you'll be able to follow the courses on one of our host sites across Europe, or in Annecy, or online. So actually, I'd like to share something with you that will summarize it all. So for the very first time, I'm going to show you the teaser video for the Grey Scott School 2026. So here's a small preview for 3 minutes of what's coming this summer.
Could a simple chemical reaction teach you how to unlock peak performance on today's supercomputers? Welcome to the Grey Scott School 2026, a free, advanced summer school on high-performance computing. Designed for professionals from industry, public sector organizations, and academia. From June 22nd to July 3rd, 2026, join us in Annecy, France at LAP, at one of our satellite sites across Europe, or online via live streaming. All courses are taught in English. You can pick the courses most relevant to you or dive into the full 2-week program. You'll learn the practical behavior of modern hardware and how to write performance-optimized portable code. Week 1 focuses on CPUs, Week 2 on GPUs, covering architecture, bottlenecks, parallelism, memory, and performance analysis. All learning is built around a single challenge, simulating the Grey Scott reaction. Simple to start, yet complex enough to stress compilers and expose performance limits. You'll explore modern tools, languages, and libraries such as C++ 17 and 20, CUDA, Fortran, Python, OpenMP, TBB, Kakos, PyTorch, and more. The school provides ready-to-use container environments for smooth hands-on sessions. Expert instructors from CNRS and CEA guide you with live Q&A and community support on Discord. Satellite sites let you learn together locally without traveling. Want to host one? It's easy with our turnkey setup, sharing the school with your colleagues and ecosystem. You'll leave not only with hands-on HPC skills, but also an official certificate of participation. And you know what? You can start early with 18 Grey Scott Thursdays webinars, weekly from January 29th to June 11th, introducing summer school concepts and new topics. Whether you're an industry professional, engineer, researcher, or student, if you have programming experience and want to push your skills further, this program is for you. Register now at cc-fr.eu and start learning today. Grey Scott School 2026, Europe's leading HPC summer school.
So thank you for watching. I hope it will make you want to join us, of course. And now it's time for today's webinar, presented by Vincent Lafage, who will introduce Fortran programming on CPUs. As always, feel free to ask questions in the chat throughout the session. We'll be happy to help and interact with you. Now I'll give the floor to Pierre Aubert, the creator of the school, who will introduce Vincent. Pierre, it's over to you.
Okay, thank you, Marie. So yeah, you might already know Vincent because he presented already at the school, but so Vincent is a research engineer at IGC Lab and basically is working on a lot of experiments, interesting also in C++, in ADA, in Fortran, of course, and in precision. So you already had the webinar on the precision. If you have some trouble on that, I encourage you to see this one, but here today we will have a look on the Fortran language, or maybe I should say the Fortran languages, because there are several types of languages. So Vincent will explain that in details right now. So Vincent, it's up to you.
Thank you. Thank you, Pierre. Thank you, Marie. As Pierre introduced me, I will go directly to the topic, and we will travel through geologic ages, getting from Jurassic Fortran to modern Fortran Furious. Fortran started 80 and so years ago, 70? Okay, more than 70 years ago, with a project of automatic coding system for the old IBM 704. It was released in 56 and first presented in February 57. So the name tells you about the project. It's a formula translator, a high-level language handling the first abstraction, the one we don't even think about, which is translating formula to evaluation tree. So people who had the experience in the 80s of playing with pocket calculators such as Texas Instruments or Hewlett-Packard with their reverse Polish notation know that to execute some computation, you have to think in terms of this tree. And the first Fortran compiler was able to do this translation automatically. So speaking of compiler, it's maybe not the oldest one, but almost. And in any case, it's the oldest standing compiler. And not only standing, but it was the first optimizing compiler, because at this period, at the start of compilation, people were not really confident that the machine would one day, and this day was already a long time ago, one day be better at performance than what was handcrafted by all the programmers. As we will see in more detail, at first it was only a language with fixed format. It was used with punch card and had some administrative flavor to it. It was definitely computation-oriented and not system-oriented, which made it a rather high-level language in the sense that is an abstraction with respect to the memory model. It's high-level relative to the hardware, and it had only a few types. It had a large economy of means, because when you have kilobytes of memory, your compiler will not have all the bell and whistle of modern ones. A lot of things were implicit typing and declaration, which proves in the long run to be a burden, because we have to explicitly tell the compiler to allow no implicit typing now. So it came from this guy, John Warner Backus, the father of Fortran. Backus is a recipient of the Turing Award in 77, and you see from the title of his speech in receiving the award for profound, influential, and lasting contribution to the design of practical high-level programming systems, notably through his work on Fortran and for seminal publication of formal procedure for the specification of programming language. So, as you see from the title, he speaks of programming style, von Neumann style, functional style, and its algebra of program. And it's only on the next year, in 78, that the next recipient of the ACM Turing Award, who would introduce the term of programming paradigm. So this style, and in fact these styles, because you see that this guy who is generally associated with the worst hours of our programming history was in fact in advance introducing a functional style and formal method. So Ken Thompson, the famous Ken Thompson, observed that 95% of the people who programmed in the early years would never have done it without Fortran, and that it was a massive step. So let's discover these possibilities. So starting with a brief history after the genesis of this language, in 66, the first standardization of Fortran occurred. So it was a young language, and it was the only American standardization with the ANSI. So we will call this kind of Fortran Paleo-Fortran. It's deep in the Jurassic era. Already in 68, the author of Basics, which is a spin-off, very limited spin-off of Fortran, described already Fortran as old-fashioned. So this will be a recurring theme. Fortran is definitely what we call an old language. It has always been old. The first ISO standardization came with Fortran 5, alias Fortran 77, which is only Archeo-Fortran instead of Paleo-Fortran. It has a lot of influence from structured programming, but from far you would not distinguish it easily from 66. So this is a procedural paradigm, procedural style, high-level language, handling the second abstraction and the control flow abstraction. Then you had the first open source translator from Fortran to C, because anywhere you will find a rather good C compiler, but Fortran compiler were not so democratic. 88 had been a missed opportunity for after Fortran 66 and 77. 88 was the logical one, but it appeared finally in 91 in what was a groundbreaking introduction of modern Fortran. So the modernization is shown by the capitalization. When you have Fortran all cap, it means Paleo or Archeo Fortran. When you have Fortran with only uppercase, you mean modern Fortran. So Fortran 90 is a high-level language handling the third abstraction, which is data abstraction, which means data hiding, modular paradigm, derived type, the equivalent of struct of record. The thing that you will see the most between old Fortran and modern Fortran is the passage to a free format, not being constrained within the 66 character between colon 7 and colon 72. This changes a lot the capabilities for, let's say, computer engineering, programming, software engineering. You have enough space so that you are not limited in indentation. You have enough space so that you are not limited in the size of the name of your identifiers, variables, and functions. So this seemingly simple change was in fact groundbreaking. 95 was the first open source Fortran compiler with GNU G77. The norm Fortran 95, which occurred in 97, in fact, introduced functional things. Dynamic allocation was already in Fortran 90, another big one. We'll see it in more detail. And then in the early 2000, we had the first open source compiler of Fortran that finally forked into the GNU compiler collection in 2003. So, as I mentioned it, the question for the last 70 years was, has Fortran the future? So here you see a paper from 85, and you recognize the author Michael Metcalfe, which is a very strong advocate of Fortran for a long time. Is Fortran really dead? Not quite. As Bernd Strustrup says, there are only two kinds of languages, the one people complain about and the one nobody uses. I feel that we can safely say that given the lot of complaints with Fortran, it enters the first category. And this is confirmed with the Archer 2 computing center in the Great Britain, I guess. Archer 2 provided usage of their computing center by language. And you see that 62% are declared as Fortran, plus more than 1/5, which is unknown, and so maybe some 10% more for Fortran. So clearly, Fortran is distinctly not pushing up the daisies. You can see more at the link below. To provide you with a kind of synoptic history of these 70 years, I provide a chronological axis on the width of the slide, on the paradigmatic axis from top to bottom. So we can see that Fortran is a multi-style or multi-paradigm language. Of course, it is strongly associated with a procedural style, with the classical control flow of 77 and 90, else and if, select case. But finally, the concept of block that you would have in C-like languages with simple curly braces only occurred in 2008 version. So procedural it is, procedural it improves. But of course, the more interesting style is modular, starting with common. So common have a very bad reputation for good reason, but they could be used in a computing, in a software engineering style as modular elements. So they have been improved by the introduction in the standard, or at least in the compilers from 77, with include that allows you not to repeat the declaration of a common. Don't do this. And the problem was finally settled in 90 with the introduction of module and types. So abstract data types can start from here. So this is the groundbreaking difference starting with Fortran 90. Inheritance, which is often reproached, oh, but Fortran is not object. Yes, Fortran is object since, if you consider modular as object by composition, since 90. But Fortran is object fully if you consider that inheritance was introduced in Fortran 03. Okay, we may yet discuss that, oh, Fortran is not object because there is no multiple inheritance, so we need some pattern to provide some way to escape this missing aspect. One big point that Fortran 90 introduced was a dynamic style. So you can have a pointer from Fortran 90, and they are not to be confused with C, C++ style pointers. In fact, we should think of them as references, because you can point to either some allocated place, some allocated memory, or a pointer to a target, in which sense pointers are more like a reference than like a memory address, a simple memory address. You cannot point to something which was not declared as a valid target to your pointer. Okay, so here I recognize that I answered wrongly 2 years ago to this question, but what occurred in Fortran 90 was both pointer and allocatable dynamic variable. So what is the difference? The pointer will survive the end of its scope, so you have to deallocate it explicitly. So when you start playing with pointers on allocatable on target, please use the sanitizer or Valgrind if it's a small enough program to check that you are not leaking memory. Pointers are used the way they are meant to be used, which is expressing indirection, expressing data structures such as trees, graphs, list, double linked list. But most of the time, if you don't really need this kind of indirection or this kind of referencing, you may prefer to use allocatable variable. Allocatable variable will unallocate themselves at the end of their scope, which is very, very convenient. Okay. And as Sébastien pointed it last times, starting from Fortran 03, you have what one calls auto-allocation. So when you have some allocatable variable and you assign it some result, it will get auto-allocated to the right size. So it means that in this case, you don't hold strongly the allocation capabilities of your compiler, of your program. The compiler does it for you. So you have to be extra cautious with lots of memory getting allocated behind your back. And as it is auto-allocated unallocatable, it means that it's also deallocated when the compiler leaves the related scope. So very powerful things. You will see in the school that we can use pointer to improve performances. Okay, and as Turing Award speech of Bacchus was speaking about it, even if old Fortran was not a functional language, yes, you could be passing subprogram as argument. It was the cheapest way to use functions as object. It really started with Fortran 90, introducing the recursive functions on the intent of the function, of the parameters. On Fortran 95, big improvement was the concept of pure function, which is clearly functional, and the concept of elemental function, which is a pure function auto-mapped to an array of whichever rank. So this is really powerful. It is improved in Fortran 23 with the notion of simple function. Simple functions are purer than pure. They don't depend on external constant. Everything should be self-contained. And in the same way, you can have simple elemental functions, which are automapping simple functions. So for the good of our school, we are interested in concurrent style. And it started in the 90s with array expression. Array expression comes from MATLAB that was initially written in Fortran 77. So Fortran 90 got this quick and compact notation as a bonus. In 95, it was improved with the for all loop that would not depend on the ordering of the execution. So that was fit for parallelism, for concurrent usage. But it was so strongly restricted, and we'll see why in more details, that it led to its current deprecation, and it has been replaced in 2008 by do concurrent capability, do concurrent loops, which are really the way to go, as we will see. So you have the contiguous keyword that also occurred at this time. So when we have concurrency, we may want to use it for parallel things. And here, OpenMP is not a part of Fortran standard, but it existed since 97. So you can practice OpenMP with old Fortran, but we encourage you to use it with a modern one. And in the same way, distributed programming exists with MPI from 94. So the difference between the two is that OpenMP will have threads, whereas MPI will have processes. So threads share some parts of memory, whereas in MPI you need to explicitly transfer the data from one process to the other. So please get a look to MPI. A lot of good Fortran has been made with this standard, but modern Fortran try to replace it with co-arrays. So my personal advice is start with some knowledge of MPI, and you will see co-arrays are a kind of high-level language on top of MPI, which is a kind of assembly of distributed programming. So co-arrays keep getting improved in 18 and 23. They are improved by the notion of team. And the last missing style that all Fortran programmer would like to have is generic, which up to now was done with pre-processing, which is not very nice, but if you really need the generic programming, it will do. You can get intrinsic generic function from 77. So don't use A-log, D-log, Q-log. Use log, and it will adapt to the kind of rule that you are passing as an argument for the result. Okay, the notion of interface that allows you to have overloading of the same name for one function starts from 90, and I expect before retiring to see the Fortran 28 template module parametric genericity arriving. For more detail, if you want to learn Fortran from scratch, I give you these two references in French, but there is the English one as well for the teaching of advanced and expert Fortran. Okay, so what we have to see clearly is that a lot of history is a lot of history of errors. In the same way as the people in the 80s were saying that basic programming is not basic programming, Fortran programming is not what we would call Fortran programming, because if you ask people, there is a supposed Fortran style. So everybody has seen the fixed column format, fixed layout from the punch card era. No indentation are common in this old Fortran style. It's not strictly compulsory, but people felt constrained by the size of their line. So indentation was not even a thing before 64. The concept emerged with Comtran, a language which was a mix between COBOL and Fortran. Okay, many people associate Fortran to all caps, but as you know it by now, the Roman Empire would write all caps and they fail. I just say this. So lots of Fortran programs also have too short identifier for the same reason. Implicit typing is rampant. There is a repetition of declaration and repetition of commands. We have way too long functions most of the time. I recently saw 9,500 statement line of code in one function of 13,000 lines. Don't do this. And of course, goto overuse, arithmetic goto, spaghetti code, you name it. But these were practices, and this is not the language by itself. So here you find in French the structure of a program thanks to the lecture I mentioned from Idris. So you see that your main program will contain internal procedures. You can also, in the old way, link it to subprograms that are not internal, so they are externals, subprograms and functions. But the modern way is rather to use some module which exposes a public part and hides a private part that can interact. Okay, so of course, we will teach during the school only modern Fortran, but for many among you, you may have to move the old wisdom of your colleagues to modern Fortran. And it is not simply converting to free format. So it goes beyond the program convert from Metcalf that you can find in the following links. And this is an opportunity to turbocharge your code, to give it more expressivity, more resilience, more clarity. So how to do this? I strongly advise the use of SPAG. SPAG is a commercial program that you can find in Polyhedron, and for people in the academics or for your hobby Fortran coding, it is free. So use SPAG. I've been using it for over 30 years, and definitely it's a very good program. So if on the left side you have some very nasty and completely unclear Fortran 66 style code, you can move it through SPAG to the right side, where you see indentation, where you see modern if expressing structure rather than a mess of spaghetti code. In the same way, here we have a slightly more modern OBACT subroutine, and it has a command. So SPAG will explicitly extract this command as a module, which is the way to go in modern, and then use this module inside OBACT. So it allows to avoid redefining the command. So you see much clearer code on the right side, and this is done automatically by SPAG. So a lot of good things can be done, and a lot of flexibility is provided to you through the spade config file. Here you have an extract of it. You can select what type of modification you want SPAG to do on your code. Of course, it is done on a copy of your code. It will, in this case, beautify, relabel, and restructure, but without dynamic analysis. And you will have symbol table output. You will have clutter checks. You will have a variable getting defined with implicit known, and you can select in which style, if it's declaration in old style or modern style. So a lot of things can be done with SPAG before getting your code in the hands of the large language models. They can also provide a lot of good things if you ask your favorite LLM to suggest you some renaming of the variable. It will extract knowledge from the code that you might not have found by yourself. You can see some really surprising things. And if you use it in this way of suggesting modification, and afterwards you only get the script, the said script, and you pass it after you have corrected it, or only kept what modification feel useful to you, it's a really good thing. So I suggest here a recipe to get through legacy Fortran. So the first thing to do, of course, and this is more software engineering than really Fortran, is you get your source code in your favorite version control system. Then you add some build elements, because a lot of Fortran code comes with not even a make file. It's sometimes a shell script that has the one big option field, very system-specific shell command, compiling command. So build make files, build CMake, use a Fortran package manager, move it to modern practices. Of course, as soon as it builds, you can test expected result. Sometimes it's missing a lot of tests, so you want to start adding tests. And the minimum test that you can do is keep the same values, check that you get the same result after and before some modification. So this is the minimum level of check that you should do. From this, you can lint your program. So if it's still 77, use ftn check, ftn chk. If it is more modern than your modern compiler, you should activate all warnings. Warning all, warning extra, warning pedantics, warning shadow, warning conversion, you name it. From this, you need to declare everything. Implicit none in all program, module, and external procedures. And if you want to be exhaustive, then you can use in Fortran the -f implicit none flag. This one is really a must. Okay, so you have also more modern static analysis with Fortitude and Camfort for modern Fortran. They are providing you different views on static analysis for your modern Fortran. They are progressing, not fully complete, but interesting. You can also have cyclomatic complexity analysis with Lizard on code duplication test with Simians. So you see there is a lot of static analysis tool that will improve the code that you produce, that will show you things that should be corrected. And then when you are confident enough, please unspaghettify, at least by parts, but you can feed your full source code into Spag and it will be improved. So some of the following advice were for the previous version of Spag, before Spag 8, the conversion to Fortran 90 and the conversion of command to module was not done automatically. So even after the basic Spag, basic unspaghettification, we had to convert every command to include. We had to convert by hand to free format or using convert from Mike Metcalf. So convert is a bit opinionated about it will not work on non-conforming source code. So then you convert each include to module. So here is a sensitive point. In Jurassic Fortran, you had no constant or no parameter array. So if you wanted to initialize an array of coefficients, you needed to fill your constant coefficient into an array. On initializing an array, at the time it was with the data statement, made at the same time the corresponding variable static. So once it was declared, it was kept the same even when leaving the scope and re-entering it. So this is the save attribute when you want to do it explicitly. And who knows why, a lot of scientists were filling even scalar, not array constants with this data argument. So this is very weak because as it is not a constant, you can have some part of your program that modifies your supposedly constant coefficient in some place, and you have no way to discover it but the hard way. So when you have in an old code static variable that are initialized, you have to check whether they are not intended as constant. If they are, you can turn them to parameter. If they are modified someplace, it will not compile. You cannot assign a value to a parameter. But here is some improvement of the code that you can do step by step with caution. Okay, so the next steps are in automatic mode. You have to declare what is the intent for all procedure arguments and parameters. It may not be obvious. The goal is to have as many parameters declared intent in, which makes them constant inside the procedures that are used. You have to declare pure all possible procedure. You have to declare elemental all possible procedure. So when you declare procedure pure, you are not allowed to stop the procedure. You are not allowed to write anything from the procedure. So you need to debug with debugger or with unit test. So it is a big change on you need to have already declared the intent of all your arguments. So this is some work. On this part cannot be automatized by SPAG. So I did not practice what the LLM can do for you in this case, but it may be a nice use to get them provide you with a list of what function can be moved pure. Here, no vibe coding. Then another point after what I told you last time about accuracy is to genericize the kind for all floating variables. So you declare the kind, the resolution of your reals in some module, and you have only one point where you will switch between float, double, long double, and quad, and maybe sometime have precision according to the C23 standard. So this provided you don't have a multi-level accuracy, which is another aspect. Also, use generic form of all functions. You should capitalize on the generic form of the intrinsic functions. No more dsqrt, dlog, and so on. And then convert all do and do loops to either elemental function calls that automatize this looping. So for all loops should be forbidden. So now write do concurrent loops. And wherever possible, use more appropriate functions. Use dot product, don't recode it with your own loop. Use norm2, use matrix multiplication, matmul, use reshape and transpose, provide the compiler with as much flexibility to improve, to optimize your intent. So some example of this modern Fortran in the context of unit test. So the NASA provides the community with a PF unit, which is parallel Fortran unit. Here you see some Doxygen-like comments for the author, the brief explanation of a module that contains a pure function that will give you the list of divisor of an integer number as in. And you have local variables, they are explained. And you have a simple algorithm that will extend a list starting from an empty list at the start here, divisor list, and getting all the prime divisor of your integer. So we want to test it, so we have a module in the PF specific format. It means that this PF format will be pre-processed before providing you the executable for test, and you have at commands, at test and at assert equal that allow you to write your unit test. So you check here that one has no divisor. You can add messages. 2 is expected to get only 2 as a divisor. It was in fact the prime divisor list. Okay, so 3 is also expected to have only 1, a length of 1 for the array of divisor, and 4 has 2 divisor, 2 and 2, and so on. So you can write this classical kata in a test-driven development way. Another example of PF unit. Here, this is another kata where we express from one integer, a positive number, its Roman numeral version, and we test it in sequence. We check that 1 provides 1, 2 provides 2, and so on. Okay, also don't hesitate using Unicode in your commands. All compiler supports it. So here you see that you can get constant const_expr, const_eval value from intrinsic function. So it doesn't work as const_expr, as you cannot const_expr one of your own functions, only intrinsics. And some compilers such as ND Fortran don't yet implement all intrinsic as this kind of const_expr. Here you specify with _PR that this is the kind of PR, in this case double precision, real 64. And you see the commands that use mathematical notation in order to be more expressive and to relate the variable names to some physical concept. Okay, so I told you that Fortran from 203 has the object-oriented capability. So here we see a module that will be in fact a class. It has a type with the private component of an allocatable array of integers, and this type also contains method. So containing methods turns the type into a class. And here we see that we can provide the same name test, for the interface as for the type, which will make it a constructor, and we link the constructor name, which is defined as a module function. It will be called, because being private, it will not be seen away from the module. It will only be seen away from the module as test, which has been declared public. In the same way, we have the final procedure, which will be the destructor, which is defined here. And we have any method that can also be pure if you want here. So 2 years ago, I was asked whether this destructor was really sensible as allocatable, as your object as allocatable component. So this is a good question, and it should be tested either with Valgrind or with the sanitizer of Flang or Fortran. So in case you have doubt about the real necessity of this destructor, please check. Okay, so we can play the usual memory scope game and write messages before the allocation, before the declaration of some variable, capitalizing on the block and block structure. So the good practices in C++ can then be turned in good practices in Fortran. Another very strong aspect of Fortran 03 is C binding. So binding comes in two forms. What we call a scene binding, it's only a way to explicitly tell to the compiler that will in turn pass to the linker the fact that we expect to call some C function that will be called with the name equal so-and-so symbol. And we declare only a wrapper around this C function. We are bold enough to tell the compiler, to the Fortran compiler, that this C function, we swear it is pure. So be prepared to some segmentation fault if your supposedly pure function is not pure from C. But you see that this way you can provide strong information to your compiler. So here we declare the binding with a decimal floating point library. In this case, decimal with 32 bits, so kind of single precision decimal. So a lot of this job of redeclaring Fortran name for C name is very administrative, and we only convert what would be a float to a real C float. So we provide the right Fortran type for the given C type, thanks to the ISO binding module. And afterwards starts a more interesting part, which is providing a high-level API from this low-level binding, and we call this thick binding. So from the previous binding, we create operator plus that, for instance, here will overload the Dex32 add function. So in this way, you can provide a lot of flexibility, but it requires some work. If you are really into detailed optimization and you have some part of your code in assembly, there is no assembly statement in Fortran, but there is one in C, so you can use the C binding to include some assembly function that you will have compiled with C. So here is the Fortran part where only the interface and the calling of this assembly function is done. The comments here are what is in fact in the C corresponding function. Okay, we can do it. I've seen no very concrete example of doing this. So we have seen a lot of what is possible in Fortran. So what is missing? Okay, multiple inheritance is not here, so you have to rely on one of the 20 and so design pattern, which is the facade pattern. There is no such thing as first-class citizen functions. What you can do is have a pointer to external functions, which is a limited way. You will also have a procedure pointer as an alternative. So in the same way, you don't quite have lambdas, but there is some proposal to the committee that is described here as an example of lambda expression. So limited usage, but why not? You also don't have exception handling beyond what are input-output exceptions and IEEE 754 exceptions. They are not played in the same try-catch way. Anyway, there is a paper by Arjen Marcus that goes into a lot of detail to mimic exception handling if you really need it. There is also no programming by contract or even a simple assert function that You can switch off with debug mode, but you can look in this Stack Overflow link that provides you a way to in fact, have your own assert, which is a good thing if you don't want to enter the frameworks of unit testing. But okay, assert, it's a good one. As I mentioned it regularly, not yet full genericity, full parametric polymorphism. It is expected for Fortran 22Y, which may be Fortran 2028. There is already a lot of work on the GitHub page I mentioned. Here are some example of codes that don't run, but that might be the future. There is also no const in Fortran. You have parameters that are more constable. In fact, if your parameter is not an array but a scalar variable, contrarily to corresponding const or const expr in C++, it will not produce a symbol. It will be replaced as if it were defined in old C, but it has still been checked with the proper accuracy and converted to the proper type, contrarily to a defined. So we have a completely different beast here, and const would be a nice addition, but you can minimize the need for this const by using intent in parameters. There are const by construct or a protected member in your modules. No variadic function in Fortran. As I said, it's not a system language. It's not system-oriented language. But if you really need some C variadic function, I don't think that printf would be the right one, but it's a good one to play with. You can define multiple binding to restricted forms of your C variadic function. You need to define one binding for each type of call to the C variadic function. And also no coroutines currently in Fortran. Okay, so I will not go into the detail of the procedural paradigm, structure paradigm of programming. Every language provides you with the same. It's only details, it's only syntax aspect. And I will focus more on harnessing the array capability of Fortran. You have array operation, the arithmetic one, and they are meant in the sense of Hadamard product. If you multiply two arrays together with the multiplication symbol, it's also called element-wise operation. So using the star product between two matrices will be a Hadamard product and not matrix multiplication. So array operations are very efficient to express high-level abstraction. If you want to map functions on array, all intrinsic functions are elemental, and you can define your own elemental function. So it provides you with very high-level expressive, and when you have reduction on your array, you can use sum and product instead of recoding it with all the mistakes that can enter your recoding with all the errors on the index, on the starting value of the index, on the ending value of the index. Here you have really a powerful tool with sum and product. You have the dot product, don't recode it by yourself. You have the matrix multiplication, matmul. Most compiler will relate to BLAS in this case, but you can also sometimes provide your specific library if you have some application with better things than BLAS. I don't think of one, but why not? You can reshape the structure of your collection, which is very powerful because the idea of multidimensional object in Fortran is that they are contiguous in memory, and maybe sometime your rank 5 tensor can be seen as a matrix where you group indices of different dimension, different rank together in order to, for instance, put it into matrix multiplication. Okay, you have the where, elsewhere, and where structure when you want to apply some computation where the mask is true and some other thing where the mask is not true. Of course, we have, when all these points are not enough, the way to go to parallel loops that are more enuplications than iteration, which are for all and do concurrent, as we have already discussed, and we see here the difference between these three levels. Array expressions are a concise way to perform element-wise operation on array. They enable implicit parallelism, they enhance readability. They generalize scalar operation to entire arrays, and they take iterations out of the picture. For all loops, the initial tentative to get parallelism into the compiler was a construct also for array assignment, but with explicit iteration. We'll see some example in the next slide. They offer more control than array expression, and they have a potential for parallel execution. So it's a kind of bridge between scalar loops and array operation. And do concurrent loop is a modern loop construct designed for parallelism. Okay, they allow the independent iteration optimized by compiler for multi-threading or GPU execution, as we will see in the last installment of the Fortran on GPU. They are most powerful and offer flexibility for complex computation. So the idea of for all was to help with parallelization, but it was not well thought, and parallelization was much more difficult than it seemed it would. So in practice, array expression, if you have ABCD4 array of real that are conformant, you can say that C equals A times B plus 2. This is a combined operation. You can also, with elemental function, including the intrinsic one, D equal S squared T of C, will compute this square root for all of the elements of C. Okay. If you want to symmetrize your matrix, let's suppose we have a 5 by 5 matrix, M equal M plus transpose of M, potentially all being divided by 2, will provide you the symmetric part of this M matrix. What you cannot do with array expression, but that for loop allowed, was, for instance, setting diagonal elements to 0. Here you need to relate specific element with a different treatment than the other. And this you cannot do with array expression. So you rely on some index dependency. Okay, so here you can also, with this second line, get a conditional decrement. You will only decrement the indexes where the value of the array is positive, strictly. So you see that for all is not only a loop between some value of the index, but you can also put a mask condition in it. So for all allows for some flexibility, but what you cannot do with for all, and that you can do with do concurrent, is taking a test inside your loop. Okay, so in this case, maybe a mask would have done it. but a mask on something that was not yet computed should not be possible. You can also, with do concurrent, include reductions on some of your variables. So you will sum the exponential of the elements of your array and reduce them into your total variable reduction with a plus reductor. And you can also have inside the do concurrent that you cannot have with a for all local variable and logic. So as a takeaway, don't use a for loop, go to do concurrent. They are much more powerful. So what you could do with for all and you can also do with do concurrent is provide the range of two different indices. So afterwards, it's up to the compiler to decide in which order it will practically loop. But you see, this is really convenient. Okay, so I will not enter the detail of this example. With distributed programs, you may want to solve classical problems such as the dining philosopher or the Santa Claus problem. And you can do it with MPI, but you can also do it with coarray. So this is an interesting exercise. When you go to the detailed compiling and executing with coarray, you understand why it is so related to MPI. Coarray is a kind of high-level abstraction on top of MPI. You have different MPI libraries, so please check the excellent lecture of the Idris colleague about MPI. They go into lots of detail. It seems to me that it's a must to have this expertise in MPI before addressing coarray. Okay, so I will quickly speak about one of the success story that was the code from a theoretician colleague. They came to me with a code that would have taken 1,000 CPU year, and they asked me to parallelize it, but I didn't parallelize it. I started with profiling, auditing the library, improving the memory management, and expressing things in a more vectorized way. All these sequential operation already provided a speedup of 55, limiting the time expected to only 20 CPU years. The program structure was a big nest of 5 nested loops amounting to between 120 million and 11 billion iterations for only the 4 inner loops. So with this kind of parallel expression, you know that your problem will be fit for this. In the bottommost loop, the spherical Bessel function were taking more than 92% of the CPU, so computing them one less time was the right way. Unfortunately, I had a lot of other issues, and I want to thank the colleague in Idris that provided me good advice. And it's only my fault that I didn't solve it because I had not simplified the code enough. And I tried with OpenMP to turn a program that was, in fact, hard to get with threads, whereas it was easy to parallelize it with processes. So my rewriting allowed them to show some vectorization improvement. Here you see all the flags you may want to get your compiler to vectorize things. And of course, you need some help from Macao to tell you that you are no good, but show during the school this speeding of the cube root function and this vectorization of the cube root function as shown here. That was rather a good one. After vectorizing, I could move my code, my Supernova code to OpenACC on GPU, which is beyond the scope of today, but you see that the ACC pragma allows you to describe to your compiler what you want to vectorize and what you want to parallelize on the GPU. Another option, and it will be described in more detail in the next expose, is about using CUDA in Fortran, which is CUDA Fortran. So it's a very different way to think about the GPUification. I will leave the rest of the presentation for the school where we will address Grayscott itself. Thank you.
Okay, thank you, Vincent, for the presentation. So we have already a couple of questions from Leonidas. First one is the limitation of the solution for use of assembly through C bindings is that it cannot be inline. You cannot inline your bindings.
Okay, so Fortran compiler has a lot of leeway. So some inlining, I can't answer on this question because it's low-level thing. So of course the compiler will not see the function by itself. I'm not good enough to tell you about the interaction between the compiler and the linker.
Okay. But maybe, of course, it's not, you cannot vectorize if, even if you set to the compiler the function is pure, and because it
yes,
cannot, it's obliged to do a call, to perform a call on the element. So yeah, maybe it's not, but yeah, you can still call the function even if it's not optimized.
We will see this in more detail when we present the cube root function on some other function that we turned to Fortran to get sure that we would have the vectorized version. In fact, we know that it's better to have everything in the compiler in these cases.
Okay. Another question from Leonidas. In addition to the replays, do you make the slide available too? Yes, they will be available normally this afternoon or at least tomorrow. For example, today's presentation contains a lot of useful things. It would be nice to have it a way to access them. Yeah, of course, we'll be able to access them soon. Maybe not today, but tomorrow. Third question from Leonidas. If I remember correctly from the introduction, Vincent, you have programming experience also with Ada.
Yes.
Are other array operations as powerful as Fortran ones?
Okay, so here we have to acknowledge that every language has a strong statement about its identity. And as we are speaking about Ada is about a very strong typing. So at first version of Ada in 83 did not have polymorphism, did not have inheritance. We can understand this because inheritance is saying, well, these types and these types, they are not the same, but we'll use them as if they were the same. And of course, this is on the frontal collision with the philosophy of Ada. Okay, so they designed a clever way in 95 to go beyond this. And array expression are another aspect of polymorphism. You express something that applies to the element and that applies to the array as a whole. So Fortran does it with grace, but Ada by default would not accept it. You are practically doing things with different types than expected. Okay, so here you see strongly opinionated languages. So you can, for instance, do slicing into your Ada array, which is not as powerful as a slicing of Fortran array. But Ada tries to be of an even higher level, so it does not make assumptions about the ordering of the indices, for instance. Whereas Fortran starts with the first index running the faster. So maybe it's strong, it's deceiving, maybe it's not satisfactory as an answer, but the possibilities of Ada with multidimensional arrays are not as important as the array expression of Fortran, at least for what I have seen.
Okay, and another question from Leonidas. Would you say that Ada have similar expressiveness with Fortran for compiler optimization of parallel constructs, or is it lacking some things?
Okay, so Ada 2022 introduced the kind of do concurrent like loops. It's a bit strange. If you see, we see languages going in opposite direction along history. So in Ada 83, you had tasks, concurrent tasks, which are a very powerful construct to express concurrency on parallelism, whereas we had to wait OpenMP 3.5, I guess, maybe even 4, to get tasks into OpenMP. So OpenMP started with easy to express parallelism, loop parallelism, that you split your full loop among different threads. It's all well and easy, whereas Ada addressed the hard problem in 83 with the task and in 95 with the protected object. So the languages there takes on its own the detail of mutexes and semaphores. So you don't have to play with these things. It's dealt at the best level. And now Ada tries to make simpler parallelism, the kind of for each loops in C++ or do concurrent things in Fortran in Ada 2022. So the problem is that the landscape of Ada got restricted to there is only one compiler that provides the modern standards of Ada. So the competition is not good for them. They don't benefit of the stimulation of competition. So yes, my message is learn Ada for getting introduced to tasking and then pushing your OpenMP capabilities to the best. All languages have their different take on the reality, on the influence our way to address the problems in different language.
Okay, we have a question from Razi. With modern HPC moving towards GPU and heterogeneous architectures, do you see Fortran cores remaining relevant compared to the model like MP-ize plus CUDA, OpenMP? Maybe it's a bit of spoil of the next presentation on Fortran, but
yes, so as we have seen from the first occurrence of the school, it has been quite easy to get rather good result with Fortran. So, sometimes it's depressing to have a high-level language because for vectorization, you need some way of controlling things at a low level. You need to tell your compiler, I want this allocated on the scope of memory, on the boundaries of memory, and you cannot do this with high-level language. You have to use tricks. So sometimes high-level language are depressing for optimization, but sometimes they are pure joy. Okay, MPI plus CUDA, yes, we can do it in MPI plus CUDA Fortran. So okay, to be more realistic, I need to say that there are things that depend on the language, and there are things that depend on the compiler. And the NVIDIA compiler, as you will see in the school, is really, really powerful with GPU. But it focuses so much, of course, NVIDIA wants to push their GPU on the GPU aspect of Fortran, that it is a bit weak on the more modern aspect of Fortran language. So we can understand why, but I'm often disappointed with the fact that I need to have a less engineered code when I when I use the NV Fortran code. So no, I don't expect that Fortran will lose much when compared to other frameworks.
Okay, maybe to complete also your answer, you made the faster GPU code in 2024 on the school, and I beat you by 1/10 of a second or something like that in 2025. It was really hard for me to get the same performances even with CUDA in C++. So yeah, you can, if you have, as Vincent said, a really great compiler, it's okay for you because you do nothing and the compiler does all the work for you, and then you get the best performances, and all your colleagues are, what's going on? So yeah, it's but you have to understand the compiler. Well, in fact, we had some trouble at the very beginning with NV Fortran, because we have to understand how it works and how to give the compiler the right advice to be sure that it's okay. But yeah, it's a teaser for the next presentation on Fortran. So a question from Adrian. Sorry, this is probably a stupid question, but there is no stupid question, of course. So what are the reasons to use Fortran today when starting from scratch without having an already existing Fortran code base? What are some advantages over alternative? Thank you.
Yes, so when you start, I would say the main red string of this whole expose, array expression are so powerful. You will not have to manage a lot of tiny details. So the vocabulary is surprising, but the syntax is surprisingly very common. So don't hesitate using Fortran. I'm against vibe coding, but all the LLM I have seen, when you ask them Fortran advices, they provide you with very clean, modern Fortran code. Okay, some of the latest aspects of Fortran 2023 are not completely in, but you don't have many compilers able to use all of these. No, really, you have kind of renaissance of Fortran that you can see, even if we can discuss the philosophy of the TIOB index. Fortran has been back from the 20th rank to the 10th, and so maybe it's 11 or 12 by now. But all this means that there is a lot of activity in Stack Overflow. There is a lot of activity on the web. There is the excellent Fortran Lang site. There is a lot of discussion on this site, discussion coming from either newbie or from experts. There is a lot of good books, modern Fortran, about modern Fortran, not only the one from Metcalfe, but the one from Serbian guy and the one from Arius Marken. So you can see that there is in fact a lot of activity from I would say 2018 to now. There is much more activity on Fortran in the 7 last year than in the 10 years or 20 years before. So Fortran is experiencing this rebirth that is nice to see and very enjoyable.
And maybe also another point, you mentioned a bit that, but in Fortran, you have tens and tens of optimized kernels already. It's not only Matmul, it's not only Adamar product. You have lots of them, and normally everything basically in terms of computation that you want to use, they are optimized with the compiler itself. You don't have to rewrite matrix product. You don't have to rewrite the sum. You just have to rewrite the dot product. Everything you want, everything is optimized well, and you don't have to worry about it, because at the end of the day, Fortran is language for to do some computing, and once you do some computing, you want to be attached to the meaning of what you want to do, not the execution. The compiler does it for you. So, and again, if you want to start a project, if you are alone and you prefer to use Fortran because it's better for you, it's okay. But if you have a team and people in the team are more fluent in Fortran for historical reasons, or maybe you are a mathematician and you don't know C++, or Fortran is better in that case. You will have really great performances without having to deal with all the weird details of the caches, of the GPUification, of the data transfer, everything like this. The compiler does it for you, and you just focus on what you want to compute.
Yes.
So that's part of the renaissance also of the languages, because a lot of people are using it for good reasons, in fact. Okay, so Razi saying thank you a bunch. Adrian said thank you a lot. Okay, I have a couple of questions also for you, Vincent, just to continue a bit. Oh yeah, maybe I will not dig into all my questions because otherwise we will be late. But maybe for the first one, when you mentioned the statistic on Arcus 2, you had 62% of user with Fortran. Do you have the details of which version of Fortran they use, or just Fortran in general, but you don't know?
So, well, it would be a good thing that I ask before the next school. Yes.
Okay, so maybe the answer this summer?
Yes.
Okay. Because it could be nice to see if people are moving to modern Fortran and just are throwing in some part, and so maybe it's evolving. Maybe you have more Fortran 90, Fortran 2, or Fortran 03, stuff like that, than Fortran 77 or something like that. But could be interesting to know.
Yes, I have a bit provocative take on this. My usual saying is Fortran, C++ is the new Fortran, because we have a lot of people coding C++. Some are doing excellent job in their coding, but they were taught in the early 2000s, and they stopped maybe at C++ 11, and it may be not appropriate to use things very elaborate that came in Fortran C++ 20, and so we have something similar in modern Fortran. Should we use the local clause of the do concurrent if we don't have details? So maybe what defines the level of language that you reach? The good thing to check is it only old Fortran, or do we have module and then modern Fortran? So we may have a lot of different answers as to what is the good classification of the various level of languages.
Oh, speaking of features of Fortran, so you said don't use common because there is includes and you have modules and stuff like this. But is there some features that are incompatible together and you don't want to use both in Fortran, or they kind of work together roughly?
So, sometimes, for instance, I think that equivalence has been more than deprecated, and you can do some of it with transfer. So it's a kind of cast for C-like programming people. And equivalence was very much used in the in a kind of union way. So when you move to the more modern expression, you need to wrap your mind around this new semantics. So sometimes you need some warm up before moving to a new Fortran version. But yes, this has to be expected. In fact, the place where you need no warm up is when you move from for all to do concurrent. Here you don't even have to change. You can replace it with grep or with sed. I mean, you can automatically translate all your for all to do concurrent. If it was working with for all, it will be working with the more modern one. Besides this, most of the time when you move to a more modern expression, you have to reflect on it. When pause, it was the first deprecated things to go into deletion. When pause was suppressed, in fact, 2 versions afterwards, it was replaced by, not exactly replaced, but you can stop with a message by now that you couldn't do, you had only stop before. So for instance, yes, another one was a lot of people used to always have a return at the end of a function. So we are not in C. If you reach the end of the function, you don't fall over into the abyss, you are returned. So return in Fortran does not mean the same thing as return in C. It's in case you would like to return before the end, then you can express return. So you can win lots of useless lines in all the Fortran code.
Okay. So yeah, you mentioned that Fortran compiler can allocate things behind your back, but I think it's a bit of a deal of the language itself. So be prepared, but normally the compiler is supposed to help you. Sometimes not, but it's rare. Sebastian has a great example in his memory allocation presentation, but yeah, it's rare. So normally should be quite okay. Yeah, once you mention you try to make as pure function as you can. That means you can normally vectorize at some point. You ask the compiler gently and should be able to write what you want to do on one element, and normally the compiler do some magics for you and not have to be bothered with that.
So in order to vectorize, you have to provide a given setup. You need some loop around your function. So the most explicit way that you can do so is using OpenMP SIMD. What was very tempting at some time was I will OpenMP SIMD some elemental functions. So when the loop occurs, automatically it will also be the vectorized loop. In principle, it should do, but first until 2017, it was forbidden by the OpenMP standard to OpenMP SIMD elemental. So the question was why? The answer is that maybe it was more complicated than expected, so they simply forbid it. The other aspect is you can get your compiler to display optimization, and it will tell you, oh, I vectorize this. As much as possible, do this, but also check with Macao. Yes, it's
always check with Macao.
Yes, it's painful. It's really hard on your ego, but check with Macao. And then vectorizing is definitely something related to low level. So you need to understand that your compiler has some limitation, and we have seen it last year when we tried at first naively to vectorize random 1, 2, 3 pseudo number counter-based random number generator. A lot of things that were expressed in C with conditional macro I wanted to express them at the high level of the Fortran language with no macro. And then it was too complicated for the compiler to, unrolling the loop, okay, but unrolling test nested inside test, no, we have to leave it to the compiler that it cannot go into such detail. So sometimes vectorization requires to write things at a lower level or with tricks rather than nice algorithm.
Okay. Yeah, we are speaking about templates, but yeah, since you have generics and you can use log or sqrt instead of dsqrt or stuff like this, do you really miss template, or you just can deal with that? You have a module, as you said, with okay, I want to compute in float, in double, in whatever precision, then I reuse it and use generic functions, and normally everything is okay.
Oh, okay.
You cannot create template function yourself, but you can use a lot of.
Okay, so my answer will be my personal and strong opinion. So one aspect that made Fortran disappear, in my view, is the lack of a standard Fortran library. So there is some effort by the community, which is progressing fast by now, to provide this. So you can program a linked list, a doubly linked list, a graph, a map, a hash map, anything in Fortran. But missing the genericity makes that you will not have by default, once you have programmed a map of integer, you will need to define a map of float, a map of float 64, a map of long double. It's not much. You can go over that, but it's an obstacle for initial start of newcomers. So in C++, you have your vector of ints, your vector of your class, just at the tip of your fingers. So this lack of genericity is a big wound. It is hurting the popularity of Fortran, in my view.
Yeah, but maybe it's for good reasons also, because I don't know if you are using an algorithm with a map to retrieve some patterns or stuff like this, and then you struggle to optimize it because of course you have a map, so it's not possible, and then you realize that at the end of the day you need an FFT or you need something more high level to get
Yes.
the information. It's better to do that in Fortran instead of struggling to have a map, and you don't need a map. In fact, you just have to change your algorithm.
The choice is very clear. So even if I was bragging that Fortran moved to the 10th rank of the TIOB index, it means, 1-2% of users in total. So it's likely that Fortran is not on a track to be the most popular language ever, and for good reason, as you point out. I think that some equilibrium has to be found here. As it is a multi-style programming language, as C, Ada, C++, Rust, the fact that you can use multiple style makes your exposure bigger. You want to address the problems of more people. Last year on the Discord, there was this meme of, the strong dog and the weak dog. And the strong dog was Fortran addressing floating point problems. And the weak and the shy dog was, don't have me treat strings. But of course, Fortran also can do strings quite well. Of course, there is no standard regex search in Fortran, but you can program it as well. So, okay, I agree with your aspect. What you say is, yes, it's not WYSIWYG language. What you see is not what you get. What you get is what you pay for with sweat, tears, and blood.
Yeah, it's a language to compute. So yeah, at the end of the day, you have to compute. But you mentioned, you did not mention here today, but there is also a possibility to have embedded configuration in Fortran, so you can read a configuration file handled by the compiler itself, so you don't have to be bothered with that. So
Absolutely.
I don't remember well the formatting, but it's quite okay for a configuration file.
This kind of thing.
Yeah, this one. Yeah, you can do this kind of magic in Fortran, because of course you don't want to pass hundreds of arguments of your program, so you can write down a nice configuration and then it's okay. Of course,
Yes.
it's not TOML, it's not this kind of stuff, but you can do nice stuff with Fortran for that.
So you find a lot of Fortran library on GitHub for JSON. Okay, TOML, I don't remember one, but you have things to address modern standard. One aspect of Fortran that is not well known is it has a very long history of input-output. You can do very tricky things with Fortran input-output. You can also have modern aspect, as we show in the school with HDF5 in Fortran. It was really 3 times faster than the default input-output. So yes, go Fortran.
Yeah, but it's HDF5, so of course it's optimized. It's the purpose of HDF5. So yeah, of course you can do HDF5 in Fortran. Maybe 2 last question, because at the end of the day it will be a bit late. So once you mentioned binding, typically you said that if you want to bind assembler, you are obliged to pass from to C. To typically you can bind a RDTSC function to get the timestamp counter of your CPU if you want to do some time measurement in cycles, or a way to do that, a chrono library or stuff like this.
Starting with Fortran 03, you had ISO Fortran env that provided you more standardized interaction with the system, interaction with the command line, interaction with the clock. So yes, there are a lot of examples. Some are given in the school, in the example of the school. So I don't. Yes, you can see the GitLab on top of this slide. You have a lot of example. I would say mostly working, but of good Fortran.
Yeah, and of course we will dig into the details in the school, but yeah, you can do some performance tests, you can do some time measurement. Of course, it's possible. Otherwise, it won't be in the school, because the point of the school is to do some measurement and to optimize computing. And yeah, a last one, just by curiosity, in fact. Well, you were talking about a really bad spaghetti code function with 1,000 of lines, and unfortunately, it's happened also in C and C++. So even in Rust sometimes. So yeah, I don't blame Fortran developer, but I wonder if there a reason for that. Back in the day, maybe if people thought that maybe function call is slow or whatever. Is there a reason, or it's just accumulation of stuff and that's bad and that's it?
Okay, so I have multiple takes on this. The first one would be, as for any other languages, scientists are publication oriented. On some of their code, they feel it's one shot. On it's I don't know. In French, we call it une moulinette. It has to work on a given file of data. We will not use it later. So something that was particularly bad for Fortran was the fact that the ancestor of root was in Fortran, unlike root as the C-int, C++ interpreter. There was a kind of Fortran interpreter in Po, the ancestor, and to produce...
Okay, so it's an historical bad idea. In fact, it didn't
Yes.
come only with C++. Okay, just to know, just to be sure. Okay.
Absolutely. But recently, there is Fortran, which is a kind of modern Fortran interpreter. So it comes with the same risk attached, but the nice way about it is it's much lighter than compiler, and so people are trying to implement things that are not yet in the compiler. So it's a playground for people that want to play the big boys games. Okay, so my first take was about this aspect of interpreted language on one-shot code. And of course, another aspect comes from that in old Fortran, you didn't have the struct or derived type or classes or objects. So you had to pass a very large number of parameters to your function. And this was discouraging. You had to... Nowadays, you see people advising you against functions with a lot of parameters. And one good way to avoid a lot of parameters is to have parameters that have a common semantic to be in the same object, and you pass only one or two objects. But this was not possible, and as a consequence, it was not popular. On the contrary, common are the ancestor of objects, in the sense that people are not programming object-oriented programming. They are programming class-oriented programming. You don't study the theory of elements in mathematics. You are studying the theory of sets. But common were a way to share an object, but they have never been used this way. People were using objects where all components were public and addressed directly for reading and for writing. So it was the worst way to use it. So when people felt that their function was too big, usually they would share a lot of data through common and saying, oh, see, I have two functions. Yes, but they are coupled through a global variable, and this is bad. So these are my two opinions about why it came to be such monsters.
Yes, so limitation at the beginning, and then you have the history of the limitation, and your colleague said to you, no, there is a limitation, even if you are in the 90, that there is no more limitation since a while. But yeah, inertia again. Okay, so we have a lot of thanks in the chat. So from Razi, for Adrian, and from Lucio. So I think we will stop here. It was a really long presentation, a really long webinar, but it was interesting. So we will stop here. So thanks everyone for attending this webinar. Next week we will not have another webinar because it will be the GTC. So there is a little pause in the webinar here. We will go back the week after, so the 26th of March, for the GPU architecture. So all the weird details about GPU architecture, how does it work? So the same as the CPU architecture, but for the GPU. And since then, have a great week, and see you next time. Bye.
Bye.